work with Shinsuke Iwao and Mark Shimozono. So let me explain the definition, basic definition of affine Grassmannian. So our basic example is SP, symplectic group, but we can, some of the basic part can be applied for any linear algebraic group like SL or S4, SO. But so O is just the ring of formal power series in one variable, and F is its fractional field. So the affine Grassmannian is defined to be the homogeneous space of this group. This is the group of F-valued point of our linear algebraic group. And this is a subgroup, the subgroup of all valued points. So this is an infinite dimensional variety of our interest. So we consider torus equivariant homology of this object. Here, torus is the just the maximal torus of our the basic group G. So it's not the torus of this group, but we just stick to the small torus. I mean the maximal torus of the original group. And the torus equivalent homology of the affine Grassmannian has a remarkable ring structure and also coproduct. So and the base ring of our ring is S. S is just the polynomial ring in finite variable. So this is also identified with equivariant cohomology of a point, right? So we are interested in the Schubert basis of this ring, indexed by certain set related to affine Y group. Okay, so let me. So this is an analog of G mod P in infinite dimensional setting with some particularly good property. So let me explain this thing. This is an infinite set that parameterizes Schubert basis of our ring. Okay. So this slide I just show you why we are interested in this kind of ring, because it is related. This kind of ring is related to quantum business in the sense that we can consider deformation of cohomology, equivalent cohomology of flag variety. So here B is a Borel subgroup of our G, and G mod B is called flag variety, and there are some deformation parameter, and quite non-trivial way we can extend the ring structure to that ring called quantum cohomology ring. And the fundamental theorem about this is given by Dale Peterson in his lecture in MIT, and it was proved by Mark Shimozono in 2010. It says if you localize appropriately, then this quantum cohomology and our affine and homology of affine Grassmannians are isomorphic as a ring over S. And we also have a nice correspondence between Schubert basis for both sides. So if you want to compute the geometric invariance related to quantum cohomology, we can also use this side. So that's the main reason we are interested in this kind of ring. Okay. So, okay, then I think I should explain what this set. This is a subset of the affine Y group. So now we consider symplectic groups. So the Y group is isomorphic to the signed permutations. Right? So our usual generators of this ring is given by Si for I from 1 to n minus 1. This is just basically the transposition, but we also change the negative elements as well, right? This, I think, is standard. And we also have a sign, the operator of sign change. So this Sn switch the sign of n. This is our finite Y group. The affine Y group is an extended one, and by an extra generator S0 associated to this kind of affine Big diagram. Then this has a structure of the semi-direct product of a finite Y group and co-root lattice. And we also have a natural length functions. So our main construction, this is an index set. So WF0 is the collection of affine Y group element that satisfy this property. So actually the set gives a nice representative of the coset space of affine Y group mod finite Y group. So this is the basic index set of our construction. So let me give you an example. Okay, so if you consider n equal 2, so obviously identity is in our set, right? So we consider this. Sorry, so we consider this. Yeah, so we call this is and the collection of zero Grassmannian elements. So clearly identity is zero Grassmannian, and the only affine Grassmannian element of length 1 is given by S0. And so S length 2, length 3, length 4, like this. So I denote this this edge. So meaning if you have a W to SIW, I put I, then I make an arrow, maybe edge, so that both affine Y group element. So we have kind of graph like this. This is called weak, left weak blue order on this set. So for example, if you consider like so S1, S0, S1, S0, this is equal to S0, S1, S0, S1. So if we can multiply from the light Si, then it decreases the length. So this is not inside our set, something like that. So if you consider n equal 3 case, the set is looking like this. So this light blue element are important because it gives a generator as a link called PL elements. And we can also notice that this part looking like index set for the Schubert classes of the Lagrangian Grassmannian. So, okay, any questions? Okay.
Could you explain again how you know which ones are pure? Are they the ones that just have a single zero?
So this light blue element are defined like so S0, S1, S2 up to Sn and go down to somewhere. I mean, so the length I, that element actually gives so if you consider the Schubert classes of this element from 1 to n, then it gives a natural ring generator of our ring. That's what I say. Makes sense?
Okay.
Thank you. So, okay. So what we want to do is to find a good Schubert polynomial. So there's some kind of special functions that can be identified with our Schubert basis, right? So so let me just briefly review the history of kind of results. The first result on this direction is given by Thomas Lam for type A in 2008. He actually identified the Schubert homology Schubert basis of the affine Grassmannian with so-called K-Schur functions. So this is the starting result. So this one was extended to equivariant torus equivariant setting by Lam and Shimozono later. And here they use kind of dual Schur functions introduced by Mollet. For type C case, other classical cases, Lam, Shimozono, and Schilling, Schilling, Shimozono gave a kind of K-Schur of symplectic type. And they identify the ring of non-equivariant homology of symplectic affine Grassmannian symplectic group as a certain subring of the ring of Schur P functions generated by this element. So you can see these elements actually correspond to this element, PL elements, right? Then they also introduce family of functions that can be identified with the Schubert basis. And they also proved a Peterson rule for these classes. And for orthogonal case, the similar result was given by Kohn. So that's the history of this kind of result. So our aim is to so generalize this work into equivariant set. Makes sense? Okay. So okay. So the basic tool or ingredients, algebraic ingredients of our construction is given by Schur Q functions. I think the most of audience are familiar with these things, but let me just briefly explain what the Schur Q functions is. We can introduce a certain symmetric functions Qi, Q sub I by this generating functions. I want to also denote this power series by omega. And for each pair of Mn satisfying this condition, we introduce a kind of quadratic expression in terms of these functions. And for any strict partition, we can define the Schur Q functions as a Pfaffian with entries of this quadratic element. So we need to choose some skew symmetric matrix of even degree. So that's our definition. Then if you consider the ring generated by this single Qi, then these Q functions indexed by strict partitions actually gives a nice basis. Yeah, that's the definition of the Q functions. And there's a natural pairing given by this formula. And here the P function is just defined to be the multiple of Q. So here the lambda is just the number of non-zero parts of our partition. So this is the Cauchy identity. Okay, this is the classical thing introduced by Schur in 1911 in order to compute the projective characters of symmetric group. So So let me explain the geometric meaning of the Q functions. Motivated by quantum immanence for least superalgebra, Ivanov actually introduced a kind of deformation of Q functions called factorial Q functions. I don't explain the precise formula now, but there are many good combinatorial expressions for these functions. But I just explain in this slide. I just explained the geometric meaning. So here the coefficients are the polynomial in our A variable. So I use A to denote the infinitely many variables indexed by positive integers. So this is kind of homogeneous element. And if you consider the Lagrangian Grassmannian, this is the sub-variety of the usual Grassmannian, satisfying the element satisfying certain isotropic condition with respect to the defining skew-symmetric form of the symplectic group. So there is a natural index. We can naturally index the Schubert classes of this variety by strict partitions. And if you consider the scalar extension to our gamma to this deformed variable, then there is a natural ring, surjective ring home from this ring to the equivariant cohomology of the Lagrangian Grassmannian. So that sends the factorial true functions to actually the equivariant Schubert class or just zero. And the parameter got just projected to this way. This is the result in this is for equivariant, and for non-equivariant version of this result is given by Plagage. Yeah, this is a geometric meaning of Q functions. Okay, so we consider the kind of dual of these functions. So let me introduce the dual of this factorial Q by this identity. So here the lambda runs for all strict partitions. So if you, we can formally define the function by this identity, then we know, we happen to know that this is a infinite sum in terms of infinite sum of P functions like this. So the coefficient is actually type A Schubert polynomial written in this form. So this is the definition of the dual factorial P functions introduced by Nakagawa and Naruse. Okay, any questions? Sorry for many complicated notation, but so my gamma hat is just spanned by these functions. They form a ring. So omega is my previous generating functions. So if we put the equivalent parameter A1, then it has a form like this. So it starts from 1 and 2 times to A1 times P1 hat. Right, this kind of, we consider this kind of special functions. Makes sense? Any questions? Okay, so in order to apply for the geometric setting in our case, we use the projection of our ring of deformation parameter to our S. S is actually the, we think of S as the equivalent cohomology of the point. So this is a natural a projection or holding. So then we tensor our gamma hat is an algebra over this thing, but we tensor with S to denote gamma hat upper S, right? So there's a funny action of affine Y group of this ring given by this. So that the generator S other than S0 is just usual. We switch AI and AI plus 1 for I is from 1 to n minus 1, and we switch an and a minus 1 in a natural way. But for the action of S0 is funny because we multiply our Cauchy element, Cauchy kernel, and we also switch the sign of AI, A1. So funny exercise is to see that the identity holds, right? Because we have this identity. I think you see this operator actually satisfies this property. So actually they give the action of affine group, Y group. This is a basic construction. Okay. So I think maybe I should explain affine Y group. So affine roots, sorry. So for each I from 1 to n, we put simple roots associated, simple roots of type Cn. I use different notice. I use a sign convention different from the usual one, but this is the just standard one. And my S alpha 0 is 2 times A1. Now I just put the null root in affine roots to be just 0, because we consider that small torus action is natural. In other words, we consider the level 0 action on the affine Y group, so associated to this affine linking diagram. So each S alpha I is our base ring is S, right? Then I think we can state our main result. So here is our gamma hat S. So gamma hat is the ring of dual factorial P functions, P hat functions. So there is a unique family indexed by our zero Grassmannian elements of affine Y group. So I put upper n to distinguish from the original P hat functions. This is a subset of our ring, and such that for the identity, this function is just 1. And we can introduce, maybe this is the main construction. So we can introduce the divided difference operators on this ring. So here we use the affine Y action in the previous slide, right? So our family of functions is just characterized by these recurrence relations. So if you have this condition, this one and this one is related by the divided difference delta I, and otherwise this map we just keep 0. So we can compute every functions starting from just 1. I will show you in the next slide the most simplest non-trivial example. And then if you consider the S span of these functions, which I denote by gamma hat upper S lower n, this is naturally isomorphic to our homology, equivalent homology of affine Grassmannian by the identification with function with the Schubert basis elements. That this is our results. So let me show you on the most simplest example. So as we see in the previous slide, the first non-trivial functions appear as a S associated to S0. It is given by applying delta 0 to just 1. But so our delta 0 is just given by multiplication of omega and we subtract 1 and divide it by 2a1. Then, as I show you in the previous slide, so because we have this identity, the result is just P1 hat. This is written in this form. This is an infinite sum of P functions, right? So if you apply, if you next apply S1, then then we get, so we can easily see. So that the one basically acting on the coefficient. So it's easy to see that we get this. This is just P2 hat. Right? So in general, these functions are different from the original P hat. But if the the length is less than or smaller than 2n, these functions actually coincide with certain P hat functions associated to certain strict partitions, but the parameter is specialized in this way. So yeah, so let me remark that our method of using delta I is also applied to type A case given by Lam and Lam Shimozono. Okay, basically that's a result. So let me just briefly explain geometric ingredient of our proof. We actually use a kind of geometry related to total lattice of type D. So here, G check is SO, odd SO, and we can we can consider this kind of variety, affine variety, as a closed subgroup, so closed subset of the product of B check and HAR. So B check is the Borel subgroup, and HAR is just the Cartan of usual Cartan. This is a Cartan of SP actually. Anyway, so we use the coadjoint action to define this variety by this condition. Then we get this kind of commutative diagram. So here we have a special ring of special functions, and we can make a natural map from here to here and also here to here. So the all of the map are naturally compatible with affine wire group action. Then we manage to prove this theorem. So I think that's it. Thank you very much.
Thanks, Takeshi. Do we have any questions? Please just go ahead or put them on the chat.
So do you think there's going to be hope of getting like quantum product formulas?
Yeah. So we can because our construction is naturally compatible with the total lattice structure. So we can make a concrete isomorphism so that in a coordinate level we can make an explicit isomorphism given by this. So we hope we can compute the quantum side by using our functions. Yeah, that's of course we want to extend this story to K theory case also. But yes, that's right. So, but we haven't much do concrete calculations so far. That's our ultimate goal somehow. Thank you.
In K theory, you expect to have the same isomorphism?
Yeah. So we have a result. We already have a result in K theory in type A. Yeah, we are struggling to find a good formulation in type C, but so far For type A, we have the natural analog of this story.